So far, I've discussed the extensions to make IPsec standards work for PQC. Now I'm going to move on to extensions to make QKD work. This slide shows how IPsec is deployed in combination with quantum key distribution. As before, we have the two IPsec gateways with an IPsec tunnel in between. We also have two new QKD devices, one on each side, that are responsible for producing the quantum safe keys. The two QKD devices use the quantum properties of individual photons to exchange keys with each other over dedicated fibers, shown in purple at the bottom. As mentioned before, we posted a webinar back in June of 2024 with details of how this works exactly. Once the QKD devices have produced a key, they hand this key over to the IPsec gateway using a so-called key delivery interface. There are two different protocols for the key delivery interface. One is ETSI QKD 014, which was standard by the European Telecommunications Standardization Institute. The other protocol is the Secure Key Integration Protocol, or SKIP, which was defined by Cisco and which they have recently documented in a public IETF draft. Most QKD devices support both ETSI QKD and SKIP. And most IPsec encryptors use ETSI QKD, except for Cisco encryptors that typically use SKIP. Both protocols are extremely similar in how they work. Note that both ETSI QKD 014 and SKIP are completely agnostic about which flavor of QKD protocol is being used. They don't care how the QKD key is produced. They're just a mechanism for handing the produced key to the encryptor. Here we see an example of a pair of QKD devices delivering a pair of symmetric keys, encryption keys, to a pair of IPsec firewalls. In this particular example, I'm showing an ETSI QKD 014 example, but if I had shown a SKIP example, it would look almost identical. Both ETSI QKD 014 and SKIP are REST interfaces that run over HTTPS. And the flow of messages is as follows. The IPsec gateway on the left first requests a key from the co-located QKD device using what's known as a GET key request. The GET key request returns the actual key value, which is secret, and the key identifier, which is public. IPsec transfers this public key ID to the remote IPsec gateway using an IKV2 message, and we'll see the details of how this works on the next slide. The IPsec gateway on the right requests the same key from its co-located QKD device using a GET key with key IDs request, and it provides, the encryptor provides the key ID in the request, and it gets back the key value. At this point, the two IPsec gateways have the same symmetric shared key, and they start encrypting the traffic in the IPsec tunnel. Here we show how the IKV2 protocol has been extended to transfer the public key identifier from one IPsec gateway to the other. These extensions are standardized in RFC 8784, which defines a new payload called the Post-Quantum Pre-Shared Key, or PPK. The term post-quantum pre-shared may seem a little bit confusing. It's called pre-shared because RFC 8784 was originally envisioned to use manually configured pre-shared quantum safe keys. And it was only later that RFC 8784 was generalized and used for quantum keys dynamically produced by QKD devices. Now, the protocol is remarkably simple. In the IKE SA init exchange, there is a use PPK notification to negotiate the use of this extension. And then the IKE auth exchange, in the IKE auth exchange, the actual key identifier is transferred using a PPK identity notification. And finally, RFC 8784 describes how to mix this QKD produced key with the rest of the key material. And this is shown in the box in gray on the right. Here we see an end-to-end example of how all the various protocols work together to use QKD in the context of IPsec. The purple arrows represent the quantum and classical post-processing protocols between the QKD devices. There are no standards for this yet, so these purple arrows are currently typically proprietary protocols from the QKD vendor. The blue arrows represent the IKV2 control plane messages for the IPsec tunnel. The green arrows represent the ETSI QKD 014, or maybe the skip key delivery protocol between the QKD device and the IPsec gateway. And the yellow arrows represent the ESP data plane protocol for the IPsec tunnel that is encrypted using the QKD key. And the sequence of events is as follows. The QKD devices are constantly producing key material. And at some point in time, the two IPsec gateways decide that they want to establish an IPsec tunnel. In the initial IKSA-init exchange, they negotiate the use of PPK keys, pre-shared post-quantum keys. And this roughly translates into we want to use QKD. The initiator IPsec gateway requests the key from its co-located QKD device using a getKey API call. Now, behind the scenes, the two QKD devices collaborate with each other to assign some QKD material that was produced to the requested key and to also assign a key identifier to it. And once they've finished doing this, the key value and the key identifier are returned to the initiator IPsec gateway in the response to the getKey request. The initiator IPsec gateway transfers this key ID to the responder IPsec gateway in the PPK identity notification, which is in the IKAuth message. And then the IPsec gateway on the responder side invokes the getKey with key IDs API call on its co-located QKD device, providing the public key ID that it received in the IKAuth message. It gets back the secret key value, and at this point, both IPsec gateways have the same shared secret encryption key that was produced by QKD. The IPsec gateways typically mix this QKD key with a traditional Diffie-Hellman key and maybe also with one or more PQC keys. And the final resulting mixed key is used to encrypt the ESP data plane.